Welcome back, everyone, to this series of lectures on the theory and intuition behind the random forest. Specifically, we're going to be focusing on the motivation behind developing the random forest algorithm compared to the single decision tree. And then we'll also throw in a little bit of history behind its development. To really understand random forests, we have to understand them in the context of an improvement off a single decision tree. So we have to answer the following questions. We need to understand, why don't we just continue to use a decision tree? We saw in the previous section of the course, decision trees are highly interpretable and they perform quite well on certain data sets. So what are the key limiting factors behind a single decision tree? And what is the motivation behind random forests, and specifically, how do they improve on decision trees? To really understand all of this, we have to think back to the construction of a single decision tree. What we're going to do is imagine a data set with features and a label. And to understand random forests, we don't really need to provide any sort of actual feature or label or numeric factors. Instead, we're just going to imagine these as color sets. So notice here on the left-hand side, I have a group of features, just displaying them as colors. And then on the right-hand side, I have the Y column, which is what I'm trying to predict, shown here in light blue. Now, if I build a single decision tree off of this particular feature set and try to predict this Y label, recall we are restricted by the information criterion we use for splitting. And in the previous section, we used Gini impurity, which is probably one of the most common splitting criterions. We could have also used information gain. Now, when you're restricted by Gini impurity, that means you could only use certain features. So we just saw in the previous section, there's no guarantee of using all features. And it's really common for a wide variety of splitting criterion that you do not use all the features in your data set. Instead, you build out the single best decision tree you can based off your information criterion. The other thing to note here is that for a certain set of rules you use to build out your single decision tree, the root node would always be the same. If you're using the same rules, that is the same information criterion, the same max depth, the same number of splits allowed, etc., then your single decision tree was always going to look the same for that set of rules, which means the root node will always be the same. And the thing to note about this root feature node is that it has a huge influence over the tree, because the entire incoming data set is always going to be split first based off this single root feature. So that feature is really influencing everything that's happening further down the decision tree. And these are the sort of issues we keep in mind when building out a random forest. Now, we already know we could try adjusting the rules for that single decision tree. We know we can change the splitting criterion, moving from Gini impurity to information gain. We know we can also play around with the minimum Gini impurity decrease needed to continue a split. We can also set depth limits, and we can set limits on the number of terminal leaf nodes. However, for every single set of rules, there is only one single decision tree possible. If you keep running that algorithm over and over again for that strict set of rules, you're just going to get the same decision tree over and over again because, quote unquote, there's a right answer for that particular set of rules as the optimal tree. So what we need to realize is, even with all these added hyperparameter adjustments, that single decision tree is still limited. There is always going to be a single feature for the root node for some set of rules. The splitting criteria can lead to some features not being used for some set of rules, and there's always the potential for overfitting to data. How can we actually improve on this? Well, in 1995, Tin Cam Ho presents the paper known as Random Decision Forests at the 3rd International Conference on Document Analysis and Recognition in Montreal. And let's think about what her paper actually showed. We're going to think back to that same data set where we have a group of features and some Y label. Now we already know if I were to apply a single decision tree to this, then I have the issue of only using some of the features, but possibly leaving some features unused, which is not ideal because that's data that I worked really hard to collect, and it would be nice if there was any sort of signal or information in that data in order to be able to use it. Now that we understand some of the issues behind a single decision tree, let's move on to the key principles behind building out a random forest. And really, in that first paper, Random Decision Forest, there was one key idea that expanded a single decision tree to an ensemble of estimators, that is, an ensemble or many decision trees making up the random forest. And here is the key idea behind random forests, and that is, we are going to create subsets of randomly picked features at each potential split. Keep in mind, later on we're going to incorporate other ideas, such as bootstrapping and out-of-bag error into the modern random forest model, but for right now, this is the key idea. Let's walk through a simple example of creating those subsets of randomly picked features at each potential split. We start off with our complete feature space. In this case, it's 5 features and the Y label we're trying to predict. And what we're going to do is choose some n number of features to randomly select for a subset. In this case, I will say the number of features for the subset is 3. Later on, we'll actually discuss how to choose this subset feature number. But for right now, I will randomly select 3 of those 5 total features. And then, using these 3 features, I will begin to build out a decision tree on my first split. Recall, the first split is the root node. Already we can see how this would alleviate the issue of having the root node feature always being the same based off your information criteria. In this case, I'm only allowed to look at the subset of the feature space, so I have to choose a feature that is found within this subset of randomly picked features. So in this case, we'll decide that based off my information criteria, such as information gain or Gini impurity, the best feature to split on at first was yellow. Now when it comes to another node, I need to decide whether or not I'm going to split again. And if I do decide, based off my decision tree criteria, such as information gain or Gini impurity, that I do need to split again, I choose another random subset of features to split on. And then I use my information criteria to decide which of these features from this random subset I should choose in order to continue on the split. And then in this case, maybe I choose orange and I actually get enough of a decrease in Gini impurity that I'm going to just go ahead and split this out into leaf and terminal nodes. Keep in mind, we do have another node here that if I decide I need to split on this again based off my decision tree rules, I choose yet another random subset of features and then choose the best feature in this particular subset to continue the splitting tasks until I've built out my tree. Because of this very powerful idea of choosing randomly selected feature subsets, I'm going to make sure that I don't actually overfit these trees. In fact, being able to choose these random subsets of features allows me to explore many different aspects of my entire feature space. Likely, I will be able to use all the features that contain some sort of useful signal, because if they do have some sort of useful signal, while they may not always be used for the root node, I do know that eventually, depending on how many trees I build out, I will look at that feature, and if it's important, I will choose to split on it, which allows me to create this forest or ensemble of many different types of decision trees, which grow out in many different ways because I know they're looking at different subsets of the data each time they have to decide on a split. And I also alleviate the issue of not using any useful features. So any feature that happens to be useful, I know if I build enough trees, will eventually get used because it would have been selected during some random subset for some split. Which means I could have these, for instance, randomly selected trees that are all using different types of features out of my total 5-feature data set. The question arises, though, is how do we actually get a response or prediction out of many models? In this case, for classification, we will simply tally up the votes. For instance, if I have tree 1 outputting y is equal to the 0 class, tree 2 outputting y is equal to the 0 class, and tree 3 outputting y is equal to the 1 class, I simply tally up the majority vote. So I can see there's 2 votes for 0, 1 vote for 1 class, so I will say the forest itself is predicting an output of y is equal to 0. And then I can also see how sure, or the probability behind what the random forest thinks the y belonging to the 0 class is. In this case, it's 2/3 probability of belonging to the 0 class and 1/3 probability belonging to the 1 class, because of the way this voting has tallied up. So I can actually not just only know the prediction output, I can also know the predicted probability depending on how many estimators or trees I have in my random forests. Keep in mind, we'll probably realistically be building much larger forests than just 3 trees. Now when it comes to a continuous label, that is a regression tasks, random forests can also output those sort of continuous labels. In this case, instead of tallying up the votes, I will simply average out the predicted output of each of these models or each of these trees. So if I have tree 1 outputting y is equal to 10, tree 2 outputting y is equal to 13, and tree 3 outputting y is equal to 11, I will simply sum those up and divide them by the number of trees, which gives me an average value of 11.3, which is what I will say my random forest is predicting for this particular data point. Ho and other researchers showed that adding the random feature subspace constraint could allow trees to grow much deeper without causing overfitting. And a more rigorous mathematical explanation of this was shown by Eugene Kleinberg's theory of stochastic discrimination. Then in 2001, Leo Breiman publishes the article Random Forests in the journal Machine Learning, which introduces a lot of the concepts we know and practice in the modern version of the random forest model, including things like bootstrapping samples and out-of-bag error, which we'll discuss in more detail in future lectures. If Leo Breiman's name sounds familiar, it's because he's one of the authors of classification and regression trees. So you can really tell that pretty much his whole professional career, he's been working on the decision tree and applications, as well as the expansions of decision trees to random forests. Let's go ahead and further explore how random forests expand the decision trees by creating an ensemble of estimators, that is, those multiple decision trees. We're first going to look directly at scikit-learn's random forest class call and see what additional hyperparameters we have compared to a single decision tree. I'll see you in the next lecture.